For our first problem, we're going to use the rational zero theorem to list all the possible rational zeros for this function. We're not actually going to find the zeros, we'll just list the rational numbers that might be zeros. The way we do that is to look at the last term and the coefficient of the first term. First, we'll find all the factors of the last term. So all of the numbers that will divide evenly into the 6. We can ignore the fact that it's negative and just look at that as 6. So the factors of 6 are 1, 2, 3, and 6. And then we look at the factors of the 3, coefficient of the first term. And those are 1 and 3. To find the possible rational zeros, we'll be making a bunch of fractions. The numerator of all the fractions will consist of the factors of 6, and the denominator will consist of the factors of 3, plus or minus all of those. So let's list those. First factor of 6 is 1. First factor of 3 is 1. We could also combine the 1 with the 3, that's a factor of 3. And then moving on to the 2, that's a factor of 6. Combine that with the 1, or combine the 2 with the 3. The 3 can be combined with the 1 or the 3. And then the 6 can be combined with the 1 or the 3. 1 over 1 is 1. And if we look down our list of numbers, we can see that we do have some duplicates of 1. The 3 over 3 is a duplicate, so we can ignore it. And that's the only one that's a duplicate of 1. And then we have 1/3. Then we have 2 over 1, which is 2. Is there anything else that's a duplicate of 2? Yes, the 6 over 3 is, so we can ignore that. Then we see 2/3. We see a 3. And we see a 6 over 1, which is 6. Finally, each of those could be either positive or negative, so we need to include a plus or minus in front of all of them to get all of the possible factors of our original polynomial. This problem is giving us some information about a polynomial, and we have to write the polynomial. What we know is that it's a third-degree function, so its highest exponent is 3. We know that 2 of the zeros are 1 and 2i. We need a third zero, and then we know that when x is -1, y is 10. So we have a point that would be on the graph of this function. The factors of the function come from the zeros. So if 1 is a 0, then x minus that 1 is a factor. If 2i is a 0, then x minus 2i is a factor. The third zero is going to come from the 2i, because complex zeros come in conjugate pairs. So if 2i is a 0, then its conjugate, which is -2i, will also be a 0, which means that x minus that -2i is also going to be a factor. X minus 2i is the same thing as x plus 2i, so we'll go ahead and call it x plus 2i. So if we multiply the x minus 2i times the x plus 2i, we get x times x, which is x squared, x times 2i, which is positive 2xi. Negative 2i times x is negative 2xi. And negative 2i times positive 2i is negative 4i squared. The 2xi and the minus 2xi are opposites. And negative 4 times I squared is negative 4 times -1, which is positive 4. So that leaves us with x squared plus 4. And we did have this factor of x minus 1. We don't want to forget it. It's still there. So we have x minus 1 times x squared plus 4. Now there's one condition we have not dealt with yet, and that's this one. F of negative 1 equals 10. So we need to recognize that there's some constant of c that's multiplying this polynomial. And if we use that last condition, we can find out what that c is. So we know that when x is negative 1, so negative 1 minus 1 here, and negative 1 squared plus 4 here, we know that the value is 10. So 10 equals c times negative 2 times 5. So let me bring it up here so I've got a little room. 10 equals c times negative 10, which means c equals negative 1. And now we can figure out what our polynomial looks like. It's f of x equals negative 1 times x minus 1 times x squared. So if we multiply these two binomials together, we get x to the third power plus 4x minus x squared minus 4. And now multiplying to get our final polynomial, we'll have negative x to the third power plus x squared minus 4x plus 4. To find vertical asymptotes, the first thing we have to do is make sure that our fraction is simplified completely, and it is. So once our fraction's simplified, we can look at the denominator of the fraction and find all the numbers that make the denominator 0. This denominator factors into x minus 6 times x plus 6, and the two numbers that make that equal to 0 are 6 and negative 6. Those two numbers that make the denominator 0 represent our vertical asymptotes. So we have the lines x equals 6 and x equals negative 6 as vertical asymptotes. For horizontal asymptotes, we look at the highest degree terms in the numerator and the denominator. If the highest degree of the numerator is larger than the denominator, then there's no horizontal asymptote. If the degree of the denominator is larger than the degree of the numerator, then the horizontal asymptote is the line y equals 0. In other words, the x-axis. And if they're the same, which is what we have here, then what we're going to do is make a fraction out of the leading coefficients. The leading coefficient of the top divided by the leading coefficient of the denominator, y equals that, will be our horizontal asymptote. So our degrees are the same. We have a second degree term on the top and the bottom. So our horizontal asymptote is going to be the line y equals 15 over 5, or y equals 3. Slant asymptotes happen when the degree of the numerator is 1 more than the degree of the denominator. That's what we have here. Third degree in the top, second degree in the bottom. To find the slant asymptote, we're going to do long division. So we'll take the x to the third. There is no x squared term in the top. There is no x term in the top, but there is a minus 1. And we're going to divide that by the denominator, the x squared minus 9. Okay, looking at the first terms, I see an x squared, I see an x to the third. I know that x times x squared is going to give us the x to the third, and x times minus 9 is minus 9x. Draw a line, change the signs, and add. X to the third minus x to the third is 0. 0x squared is 0. 0x plus 9x is 9x. Bring down that last term, And 9x is a smaller degree than x squared, so we're done with our division. So we know that if we would divide this, we would get x plus 9x plus 1 over x squared minus 9. The slant asymptote is coming from this remainder. So the slant asymptote is the line y equals 9x minus 1. To solve the polynomial inequality, the first thing we have to check for is whether there's a 0 on one side of the inequality sign, which there is. So that means we can go to our next step, which is to factor the x squared minus 6x. So that factors into x times x minus 6. We're going to find the numbers that make each of those factors 0, which happens when either x is 0 or x minus 6 is 0. So we have two numbers that are boundary lines for the signs or the sign changes in our inequality. That would be at 0 and at 6. Now I know that this inequality is equal to 0 at 0 and 6, but I want to know what happens in between those numbers. So I'm going to make a sign chart with the 0 and the 6, kind of like a number line. And then I'll put the factors that those came from over here on the left side. So they came from the x, and they came from the x minus 6. I know that x is 0 at 0. And when x is less than 0, then x is negative. And when x is greater than 0, then x is positive. X minus 6 is 0 at 6. And when x is less than 6, then x minus 6 is negative. And when x is bigger than 6, then that x minus 6 is positive. I want to know the sign of the product of those factors, so I'll multiply the signs straight down. So if I look at the interval that is less than 0, I have a negative times a negative, which is positive. When I look at the interval between 0 and 6, we have a negative times a positive, which is negative. And for the interval bigger than 6, we have positive times positive, which is positive. Those are the signs of the product, and what I'd like to know is where is that product greater than 0? And that's happening here and here. Actually, it's greater than or equal to 0, which means it does include the 0, it does include the 6. So to graph that solution, we can just take what we see in our sign chart and translate it up here to the number line. So 0 and 6 are where the product is equal to 0. So we are going to include those. And then when we're less than 0, so we're including 0 and everything to the left of 0, that product was bigger than 0. And then including 6, because 6 was equal to 0, our product was also positive. And then to write that in interval notation, we have numbers from negative infinity up to 0, including the 0, union numbers from 6, including the 6, all the way up to infinity. Now to find the solution for the rational inequality, the fraction, we're pretty much going to do the same thing that we did for the last problem. What we have to be careful of, though, is that we never let the denominator become 0, because that would be dividing by 0, which is undefined. So we'll just keep that in mind when we look at what our solution is. We can still find the numbers that make the numerator and denominator 0. So the number that makes the numerator 0 is 6, because 6 minus 6 is 0. And the number that makes the denominator 0 is negative 8, because negative 8 plus 8 is 0. So those are the two numbers where we know numerator and denominator are 0. We can make a sign chart to determine what are the signs in between those numbers. So negative 8 and 6 are the two numbers that are defining our intervals. The factor in the numerator is x minus 6. Denominator is x plus 8. X minus 6 is 0 at 6. All the numbers that are less than 6 make x minus 6 negative, and all the numbers that are bigger than 6 make x minus 6 positive. And for x plus 8, it's 0 at negative 8. Numbers less than that make x plus 8 negative, and numbers bigger than that make x plus 8 positive. Now we're going to multiply the signs, even though this is division, because the sign rules for multiplication and division are exactly the same. So a negative times a negative is the same thing as a negative divided by a negative. It's still going to be positive. Negative times a positive is the same thing as a negative divided by positive, which is negative, and positive times positive is positive. So we want to find numbers that have a quotient that are positive, which means we're looking at this interval and this interval. So let's go ahead and graph this. We know that negative 8 and 6 are defining our intervals. Do we want to include those numbers? Well, we definitely do not include the negative 8 because it makes the denominator 0. But we don't include the 6 either because this says we want numbers greater than 0, not equal to 0. So we are not going to include the negative 8, although we are going to include everything less than that, because our sign chart says all the numbers less than negative 8 will give us a positive result, and we do want this fraction to be greater than 0 or positive. And we don't include the 6 because this is not greater than or equal to, it's just greater than. So we want all these positive values, but we don't want the 6. And then to write the solution, we would say we have everything from negative infinity to negative 8, not including either one of those. Or we have everything from 6 to infinity, not including either one. To graph this exponential function, we're going to make a table of values for x and f of x, which remember is the same thing as y. I'm going to try negative 1, 0, 1, and 2. So when x is negative 1, we get 5 to the negative 1, which is 1/5. When x is 0, we get 5 to the 0, which is 1. When x is 1, we get 5 to the first, which is 5. And when x is 2, we get 5 squared, which is 25. So you can see our function's growing very rapidly. We've got 0, 1, 1, 5, 2 25's way off the chart. Negative 1's getting really close to the x-axis, but not quite there. So we're going to skim the x-axis. We're going to hit that y-intercept, and then our graph's going to climb very rapidly. To write this log equation in exponential form, we're going to take that base, bring it over to the other side, and keep it a base with the 2 as the exponent. So we get the exponential equation b squared equals 49. To write the exponential equation in log form, we're going to take the base of 8 and bring it on the other side and keep it a base, but now it's going to be a base on a log. So we get log base 8 of the x equals the exponent, which is 5. For the domain of a log function, we just have to remember that what we're taking the log of, the x plus 4 in this case, has to be positive. So if x plus 4 is positive, then x has to be greater than negative 4 for our domain. Now let's find the exact value of each of these logarithms, starting with log base 8 of 64. I don't know what that is, I'll just call it x, and then I'll rewrite this in exponential form. So I know that 64 equals 8 to the x power. Now if I can get the bases to be the same on both sides, I'll be able to solve this. And I do know that 64 is 8 times 8, or 8 squared. So if 8 squared equals 8 to the x, then since my bases are the same, my exponents have to be the same. So x is equal to 2. So the log base 8 of 64 is 2. The next one's a common log. So just to make sure that we know what the base is, let's rewrite it. The common log is a log base 10. And 1/100th is the same thing as 10 to the negative 2 power. We have a property of logs that says that if the base on our log, which is a 10, is the same as the base of the expression we're taking the log of, which is 10, then that simplifies to just the exponent, which is negative 2. A natural log is a log with a base of e. So let's rewrite it that way. Natural log is log base e, and we're taking the log base e of e to the 8th. And now just like the last problem, we're taking a log with a base of e, and then we're taking that log of something with a base of e to the 8th, which means we have a property that says that equals just the exponent, which is 8. Now let's use properties of logarithms to expand the log expressions. The first one is a common log, a log with a base of 10. So for now I'm going to write it that way. I'm going to say it's the log with a base of 10 of, and we have 1 million, which is a power of 10. It's 10 to the 6th power. That's multiplying an x, and there isn't much we can do with the x. But we can notice that we have a product. So we have a property of logs that says the log of a product is the sum of the logs. So this is the same thing as the log base 10 of 10 to the 6th plus the log base 10 of x. Finally, the log base 10 of 10 to the 6th is just equal to the exponent 6, and log base 10 of x can't really be simplified, but we may as well go ahead and just write that as the common log that it is, log of x. For our next problem, we can notice that we have a log of a quotient. So we do have a property that says a log of a quotient is the same thing as the difference of the logs. So this is the same thing as the natural log of e to the 6th minus the natural log of 19. Because natural log is a log with a base of e, and let's write it that way for the moment, we can simplify the first term. Because the natural log, the log with a base of e to the 6th, is just the exponent, which is 6. And then we have minus the natural log of 19, and that's as much as we can do with that one to expand it. Our last problem is also a log of a quotient, so let's use the same property we did in the last problem and rewrite that as the difference of two logs. So this is the log base 5 of 25 minus the log base 5 of the square root of x plus 4. Now let's do a little work with exponents. We know that 25 is the same thing as 5 squared, and we know that a square root is the same thing as a power of 1/2. In the first term, we've got a log base 5 of 5 to a power. That simplifies to just the power of 2. And in the second term, we can bring that power of 1/2 down front and multiply it times the log base 5 of the x plus 4. And that's as far as we can expand that expression using properties of logs. Now we're going to use those same properties of logs, but in the other direction, we're going to do it to condense these, to put the log expressions together. The first one is a difference of logs. Difference of logs is the same thing as a log of a quotient. So this is equal to the log of the quotient of 4x plus 1 over x. For the second problem, let's take that 1/8 that's multiplying the natural log of y and put it on top of the y as an exponent. We've got a property of logs that will let us do that. So the natural log of y to the 1/8 plus the natural log of z. And now since we have a sum of two logs, we can rewrite that as a single log of a product. So the product would be y to the 1/8 times z. And now let's solve some exponential equations. For the first one, if we can get these bases to look the same on both sides of the equal sign, we'll be able to solve very easily. So the first thing I notice is that 27 is 3 times 3 times 3. So 27 is 3 to the third. That's being raised to the x power. On the right side, I see a square root of 3, which I know is 3 to the 1/2 power. Back to the left side, we've got a power to a power, so we can multiply the powers. So 3 times x is 3x. And on the right side, let's go ahead and rewrite that with a negative exponent. So 1 over 3 to the 1/2 is 3 to the negative 1/2 power. And now that the bases are the same, the exponents have to be equal. So that means the exponent on the left, the 3x, has to equal the exponent on the right, negative 1/2. And if we multiply both sides by 1/3, we'll have x equals negative 1/6. For the second problem, let's also see if we can get the bases to look the same. So on the left side, I don't think there's a whole lot we can do. That's e to the x plus 2. On the right side, we can certainly rewrite that as e to the negative first power. And now that the bases are the same, the exponents have to be equal. So x plus 2 has to equal negative 1, which means x has to equal negative 3.